Well, welcome everyone. This is Fred Schenkelberg, and Colleen, appreciate you here again. Hope it works out for you this time. And Sam and Randall and Alex, a handful of others, and us have been chatting a little bit about what reliability means to customers, and that's really a heart of reliability engineering in my mind. But let me go ahead and get the slide deck loaded here, and we'll get started. I'm going to leave the chat window open. And Colleen, that's good to know that you can hear me this time. I'm going to leave the chat window open, and I'll have a Q&A window open most of the time. So hopefully if there's any questions or if you've got comments or feedback, and I'll be prompting you occasionally through the session for input. My intention is to make it not just a lecture, but to get your input and your experience included in this discussion today. I want to mention as we get started that this is the first part of a 12-part course I'm planning on running over the next 12 weeks. And I'll have I think there's a link. Let me bring back up the lobby. There's a link in the bottom right-hand corner, information list for the reliability management course. If you click that, you'll be able to register for it. It's a MailChimp email list, and as I get my act together and some of the infrastructure in place, I'll be able to provide more information about this course as it gets set up and ready to go. But I expect to have the second installment next week for those that are interested, and then we'll go on a weekly basis through the summer. And Ignor, I'm sure I'm not pronouncing that right. Thanks. Welcome coming in from Turkey. I know that we've got a handful of different people in Europe and the Middle East. I think even Africa is represented today by some of our participants. But I'm basing this whole course and this introduction, which is an overview, and I'm going to try to highlight some of the very key points that the reliability engineering management is. It's sometimes a management role, sometimes it's an individual's role, sometimes it's a design engineer's role. Yet in the course of creating a product or servicing a facility or a plant, reliability happens. Things fail, things are repaired, things are maintained, items are returned on warranty, and so on. The reliability of our products or of our assets, it is what it is, and we do a lot of work to design and build and create systems such that it is minimize the cost of unreliability is probably the right word for that. And I'm struggling a little bit because I know I've got a couple of extra slides here that are going to try to define this a little bit, and I do struggle with defining what is reliability engineering. It is a discipline. We've got a unique body of knowledge. The ASQ Certified Reliability Engineer gives us a body of knowledge. There's also the Association of Maintenance Professionals has a certified reliability leader, and they have a body of knowledge that overlaps quite a bit. The Society of Maintenance Reliability Professionals, SMRP, if I remember that acronym correctly, also has a body of knowledge, and it's a little bit more focused on plant and maintenance, yet they also have a certification. And I just saw a note from Sean saying they're only hearing music. Is anybody else hearing me talking and not just the music? Make sure I turned the music off. Okay, so we're good. I'll just make sure I turn that music off, because that would be annoying if it's still playing. Yeah, it's off. All right, let me drive on here. Thanks everybody for the feedback. So reliability has some definitions of what it is and isn't, yet I'm not really happy with that the definition Society of Maintenance and Reliability Professionals. Thank you. Thanks, Greg. Reliability is more than just a list of tasks and tools and techniques that we use. It's more than just the statistics that we use to do data analysis, for example. And I think that's missing from a good number of the different definitions that are out there. I think the AMP's has a pretty decent definition of it, where it's to provide leadership and to provide value. But what do you use? How do you define reliability engineering? And my next question really is going to be after this is then how do you describe this to somebody else? So you can use the chat window and just give me what you think. What is reliability engineering? I have a little note that says multiple attendees are typing, so looking forward to your input here. Thanks, Greg. Yeah, managing the physics of failure. Conformance, Rajesh. I've seen that quite a bit, especially from more on the quality side of areas. Work is intended, meet customer requirements, business excellence and success, application of skills, series of activities leading to improved perception of quality. That's an interesting one, Greg, or George. Influencing the design. Now we're talking. I think a handful of these comments really do tie it into a business or the organization, whether it's a military organization or a paper mill, oil refinery, or a product going out to the Christmas market. It's a contribution back to society to minimize failures or the cost and consequences of those failures. But we do that through influence. And I'm looking real quick as Jim, you mentioned influencing the design or in some cases the maintenance program. We're often not, as reliability engineers, the decision makers. We influence or contribute to a larger group that does make these decisions. Yeah, make the product insensitive to noise. Nate, that sounds like the Taguchi type spin on this, which is a very useful tool. Probability of success. Ed, you must be in the more of a military type area. Probability of mission success. There's costs associated with mission readiness and equipment and training and redundancy in systems and so on. So I tend to focus on cost as being the value, as kind of the denominator we use. So a parallel question here. Thanks everyone for the input. I appreciate that. Another one is, and I posted this to the ASQ Reliability Division LinkedIn forum a couple of days ago, is how do we describe what we do? And one of them I found was enjoyable, and I've used it myself a few times, is somebody says, so what do you do? And I says, well, I break things. You know, I'm still 8 years old taking apart my mom's toaster. And that's what I do for work. I know it's much more complicated than that. But if you meet somebody that's not in our profession or in the groups we work with, how do you describe what we do? So sitting on an airplane or waiting for the train, you meet somebody and it's a pretty common question. It's, oh, so what do you do? You know, how do you answer that question? Break things scientifically. That's a good modifier on the way I think of it. And you can tell from our previous set of comments and questions, it's a bit more than just breaking things. And breaking it scientifically is probably as succinct a way as I would put it. make it work when people want them to work. Yeah, I agree. Probabilities, we do some math, we do some statistics, optimizing uptime. I agree, Amanda, that's a good one. Yeah. Estimate performance under expected environmental stress. Ignore it. You're touching on what I'm going to get to in a moment is what I call the reliability definition or the reliability goal, and it's in most of our textbooks that we do. Uncover failures to avoid them. Yeah, Vipin, I have found so many engineers I work with in design and development that are intuitively designing away from failure. And so what we often do then is help them find those failures or find the faults or find the weaknesses. And it could be just a lack of margin, for example. Yeah, the breakdown devil's advocate, Jack. Yeah, it reminds me of a role I had one time where I was a design for manufacturing engineer at a factory, and the design guys were in the same building. And when I talked to them, I told them that we didn't have the equipment to build it that way. So they were always upset with me that we weren't redesigning manufacturing to cater to their design. And then vice versa, the manufacturing folks didn't care to see me come around because I was always bringing in these new processes, new equipment, new design constraints and problems. What I found, though, even as a design for manufacturing engineer, is if I could talk about the improvement to reliability, the reduction of failure rate to our customers, I could win the argument because it had such an impact. It was so much of a value to our organization so that it became a good part of it. Oops, Sam, can't hear a thing. I'm not sure. I'm not sure what the deal is. Let me double check. I think everything else is looking good. So if I hear that from anybody else, I'll say that. But the notion of what we do and how we describe it and what is our scope, what's our purpose of being a reliability engineer goes to the heart of how we manage it and how we manage the role of reliability engineering within an organization. So it's in some places I've heard people say, well, we do product testing, and others say that we do risk analysis. And I know in some organizations it's very segmented or sliced up as to what a particular person or group would be doing. But the notion is that reliability engineering really addresses a great broad area of the organization, everything from marketing to how we advertise and understand what our customers' needs really are, to how we sell the product, how we attribute its performance over time. But it also is in what components we use, what materials we use, what manufacturing processes we use, the suppliers we work with, and so on. Reliability and reliability engineering has quite a bit of influence on all of those different areas. I'm going to come back to this question is how is reliability of value to your organization? And for people that have seen me present before on value, it was a couple of months ago, or have been part of one of my courses, I regularly talk about that if we're going to do something in reliability engineering, whether it's design a test or doing a risk assessment, it should be for some purpose. It should have some tangible value back to the organization. Oftentimes that involves decision making, and oftentimes it's easy to characterize by reducing failure rate or reducing the cost of maintenance. So the idea of reliability is pretty broad, and how do you manage that? How do you put that all together? So one of it is by thinking about, well, what is our role? What is it that we do? And I alluded to it a little bit with those previous questions. In a succinct way, I think of it as that we enable good decisions. And I'll come back to that point in a little bit. Let me give you an illustration of one that I know that didn't work so well. I used to, when I was at Hewlett Packard some years ago, I had the opportunity to talk to a lot of different teams and engineers from across the corporation about reliability. And one of them, as I talked to the double E's and the mechanical engineers about the reliability program, they said, "Oh, Mohammed, he does that." And Mohammed was their reliability engineer. He was pretty skilled. He did predictions, he did FMEA work, he did process control type work. He helped them to design a reliability test. He worked with vendors. He was pretty busy. And part of it is that he did everything. And so everybody else in the organization said, well, the reliability guy will do that for us. And so Mohammed was working, I think, on the order of 70 to 80 hours a week, just attempting to keep caught up. And he had enough of that after a couple of years, so he went across the street to another company and took a different job, and he was still in the reliability realm, but walked out of the organization he was in, and took the entire reliability program with him. Now, he was doing a great service to that organization and answering a lot of good questions and providing a lot of information, but I would say that's not really his role. Randall, he represented a single point failure for their management of reliability engineering. I look at it as, and I've found very successful organizations where the reliability engineer is more of a coach. They're in providing the structure, say the information on the cost of failure, or the tools of doing risk assessment, whether it be FMEA or hazards analysis or whatever, but also very much teaching the rest of the organization how to do that. So that if an electrical engineer needs to talk to a vendor about derating options, they can do that because they understand what derating or design margin is about. But if like Mohammed did, is he just did the work. So the electrical engineers never knew how to talk that way with their vendors or how to consider the proper derating factors to put on their products. They didn't wrestle with that or understand it. So I've seen organizations where the reliability professional did everything. And it's a risk, a single point failure, as Randall pointed out. Whereas I think our role is more on the coaching side or mentor side. And of course there's a balance. There's times when we certainly have to roll up our sleeves and get to work. But I'd like to preserve that for the depth of knowledge that we bring to the table. A sophisticated accelerated life test or a complex data analysis exercise, and provide that information back to the organization. But many of the day-to-day tasks and the many decision points that make up a design, it's not possible to be there for all of those. So our role is to expand the knowledge of reliability engineering in these tools such that others can use it effectively. And then, so coaching is probably the best word that I know of. To illustrate this idea of this point of decision is, in most organizations, there's time to market is ship it on a particular date. There's a schedule for the development of the program, or there's a schedule to bring the new line up to speed or up to production. There's the cost, the bill of materials cost, or the cost of maintenance of an asset. And then it's what it does, the features or functions and so on. In some organizations, it's features. They want to be the cutting edge technology. They use the greatest, newest, coolest stuff. Cost isn't so much an objective. Time to market is probably important but not critical. Another example I've run into is the consumer market that are preparing to sell something in the Christmas or the holiday market. And so they work all year, good part of the year, and in the summer start production, because if it's not on the shelves, they don't sell it, and they lose that opportunity to sell their products. So time to market to start production and get it on the shelves is absolutely critical. And they'll give up features, they'll give up cost, increased cost, I should say, to achieve getting it to market on time. Those are the three classics. It's feature set, cost, and time are the three resources that every program team generally has to deal with and prioritize. Now, when I ask the question of how do you rank order these and add reliability, how would you rank order these? What's the number one in your organization? What's the number one priority? And is that clear? Is that universal across your organization? I'll say that rhetorically. So jump on the chat window and what's the top priority for your organization?
I don't have those two.
Yeah, all aspects need to be in balance, Randall. I agree that that's the goal. Yet let's say you've met the threshold for nothing's a showstopper. The reliability is good enough. We look like we're on schedule, and I still have to make a decision. What's my priority? Time to market, time to service, availability, time to market. And I know from our previous chat, I know there's people here in the oil industry, there's a paper mill, there's a couple of product people. I think there's somebody from Google. I'm not sure what part. Uptime, availability, cost and schedule. A handful of you, uptime and availability, are getting close to this reliability concept. It really depends on your market and depends on your product. And it's not always reliability or availability as the top priority. Now, I know a good friend of mine was working at the NUMMI plant, as a Toyota factory that was here in the Bay Area that closed a few years ago. And he said that when a welder went down on the manufacturing line, it stopped the line. And they knew that every minute it was down, how much of lost sales that represented, because they weren't able to produce some portion of a vehicle in that minute. And so they knew what the cost of downtime was, and it was very, very clear. So they knew what it took, what kind of spending they could use, or what kind of a priority it took to get the line back up and running again. Whereas when I'm working with a product team, say a medical device, and they're going to make a few thousand of these things a year, they will say they want good reliability, but they don't have a good figure of merit for what does it cost when it goes down. So that becomes an issue, is how do you balance time to market, cost, and features with reliability? Now, in organizations that uptime or product throughput is known and quantified, it's pretty obvious. It's balanced pretty directly. Yet in many organizations, it's not well known. So if time to market is the factor, you'll probably know that every day of missing the target is a day of lost sales, and there'll be some number of lost revenue from that. Well, what happens if half the products fail as they're being sold? Is it worth waiting a couple of weeks to get it right? What's that balance or trade-off? Well, in that case, you need to know what's the cost of unreliability, what's the cost per failure, for example, and failure rate, a few other pieces of information. So if you take nothing else away from this presentation, it's this concept that creating a balance, a way to compare and contrast the trade-offs of these four features or priorities for a design team or for a factory is essentially reliability engineering management. If it's worth doing, it's a balance then against, do I reduce costs of the product or do I increase reliability? Where's the better investment? What's the better return on investment is one way to put it together. So it's a pretty decent way to think about it. At least I think so. So let me dive into that a little bit more. So I want to tie these two concepts together a little bit first, though. I read a book years and years ago called The Agony and the Ecstasy, and it was about Michelangelo, if I remember the right artist. And he created David, and it's a biographical novel. I think it had a lot of factual stuff in it, but I'm sure it was fictional, where the writer said that the expression on David and the statue of David is from the story of David and Goliath. And many of the previous artwork and statues that were made showed David being triumphant and defeating Goliath, or in the act of the battle. Whereas Michelangelo said, I'm going to create a statue at the moment David decided to go battle Goliath. It was the point of decision that he was ready to go. And in reliability, it's that point of decision that occurs throughout your organization is how reliability is created, is accomplished. When an electrical engineer picks one component versus another one at some derating value or some quality of component, it comes with a failure rate, whether or not that person knows what it is. So connecting in that balance, that previous slide, is if they understand the consequence of changing the failure rate to the good or to the bad, it may influence that point of decision, or may influence what they do. I've heard people say, oh, we know it's going to run 30 degrees Celsius hotter than ambient, but that's okay, we'll put a fan on it. That's a point of decision. And whether or not a fan actually gets added or not, they've increased the risk by running the equipment hot. And so it's, how do we influence all of those points of decision? And so what I'm thinking is that it's certainly by what we measure, what we talk about, the program plan, and the dissemination of the information, such as the cost of failure, or what's the impact of failure rate, how do I calculate that, what's its magnitude on warranty or on downtime, so that people can make good decisions. And it's really the heart of what we do, is influence that point of decision. We do that in our relationship. As I mentioned right at the onset, we rarely are in a position of authority to make the final decision. We may have great influence, but we do that by building trust and credibility, by being gifted, or not gifted, but competent in our skills. We know the statistics, we know the failure mechanisms, we can design tests and report them accurately, we can just converse with vendors to understand where the risks are, and so on. At the end of our work, though, is that we're working with the rest of the team to make trade-offs and find that balance. And that's reliability engineering management. It's taking all those tools and techniques we have, embedding that into the program and the rest of the people we work with, such that they get the most value out of it, in balance with all the other priorities that the organization has. So, does that make sense? I'm going to pause here and just see if there's any questions or comments on that concept. Does this sound familiar to what you do already, or is this a little bit different? And I know that the chat window has been rolling up, so I'm going to spend a moment and catch up with some of your comments. Yeah, Randall, it depends. Trained as a statistician, I've tried to avoid saying it depends, because it usually irritates the other folks I work with. Well, what is the balance? What is the variables that we got to deal with? So Mercedes I agree it has to do high quality and reliability over cost, for instance. It's just as important for Volkswagen, though, is they have a thinner profit margin, and they're selling it at a different price point, yet the car still has to last. So it might be a different set of constraints and balances, yet the same basic approach still applies. Yeah, Myron, thanks. Common sense? I hope so. Marianne, yeah. How many organizations believe it? That's a good question. In my experience, and I've worked with about 150 to get probably closer to 200 these days, I haven't tallied it up in a little while, of different organizations of how they prioritize and talk about reliability. It's not many do it really well. Now, that may be because companies that are doing well don't call me, so I may have a skewed sample here. Committed to it. Yeah, Jeff, every organization knows they create a product that comes with reliability, or they produce a factory line that has a inherent availability built into it. It's oftentimes it's when you have a disaster or a major problem like a major recall that they all of a sudden they got to pay attention to reliability and measure it and track it and follow it. This ties in a little bit with this programs and projects. I'm going to separate these two just slightly. Programs is more on the organizational level, the structural elements of a reliability program is, well, what is your failure analysis capability? What is the, how do we interpret what customers tell us in a grand scheme of across our portfolio? How do we position our product in the market? Is more program-related type decisions. Projects, I think of it as a specific product, as a specific brand or a model of Mercedes, for example. Yeah. Brian, you're right. There's thousands of decisions, and it's how do we influence those is a huge piece of it. So part of it is the programs we put in place. How do we include the key elements in product development life cycles, like in the checkpoint meetings? We often say we're going to set goals early in a program, and then we have different milestones where we're measuring it. Well, if we don't have a way to capture data and report it from previous projects, it's difficult to use that information, which is usually the best information, to get an estimate of our current design. And then on specific projects is how do I use, say, a block diagram to aggregate the information from vendors, from estimates, from past programs, from past field data in order to create an estimate. So the programs is the structural elements and the projects is the tactical elements. Do I need to run a halt test this time? So programs would be, do we use a checklist, which I don't recommend, by the way, for a project? And what's the types of things we should include at various points across the project? That's program structural elements. In a project, I'll go back to that, should we do halt testing? Well, if I've got a great list of what needs to be fixed on this program and we're doing a cost reduction program or a reliability improvement project, I probably don't need to discover new things. It's probably not going to yield a lot of good information. But if I've got a brand new power supply from a new vendor, a new technology of some sort, well then highly accelerated life testing may be really valuable to uncover or discover failure mechanisms. So there's a balance of decisions both at program level and at project level in every project. The tactical part of reliability engineering management is building the programs to support the ongoing projects. And then at a project level, it's the tactical decision making and influence that we bring to the table when working with the rest of the organization to develop a particular product or product line. So early on when we were talking about what is reliability, And I know that any of you that have opened up a reliability engineering textbook, whether it's the Pat O'Connor's Practical Reliability or Iris Coombs and Moss, the Handbook of Reliability Engineering and Management, and there's many others, is they almost all start within the first page or two with a definition of reliability. Usually it has 4 elements: the function, environment, probability of success, and a duration. So how does your organization talk about reliability? What terms do you use to describe reliability? And I saw a little bit earlier uptime and availability, but part of that is reliability. What do you use in your cases to distinguish a non-repairable system, say a motor in your line? What reliability does it have to have? How do you talk about that? How do you quantify it? Repairs per unit, so like a failure rate. Yeah, when I was at MTTF, FIT, when I was at HP, we used annualized failure rate, and to compare different product lines from high-end, very expensive servers to hand calculators, we divided it by the sales dollars, essentially, to normalize it. Incidents per thousand, MTDF, not sure what that is, but it's probably similar to MTBF. Rejected products, number of failures, B10, it's the 10th percentile, is when the point in time when you have 10% of your failures. Percentage of rework, it's often a good indicator of how efficient your line is and how in spec and well it's performing. What I'm looking for is a couplet, really. It's duration and reliability confidence. Nate, I think you look familiar. I know you from somewhere. You've probably heard me talk about this a number of times and probably know what my next slide is. Anybody that's seen my work in the past knows I don't like MTBF. I consider it the worst 4-letter acronym that we have. So I won't call out names, but if you're using an MTBF or a variant of that, I highly recommend that you take a look at the site nomtbf.com. Let me add it to the chat window here. Where I have an ongoing blog and a handful of other people have contributed and a couple of essays about why I feel so strongly about that. It's a bit beyond the scope here, but keep in mind that MTBF and variants of that it's the inverse of the failure rate. It's just the probability section of what really is a 4-part definition. Now, many organizations, say you're working on the iPhone over at Apple, or I know we've got some Google people here, so let's say you're working on a phone or a website. There's a function. This is what it's supposed to do. So Gmail is supposed to allow email communication. A phone is for phone calls and apps, for example. And then there's an environment. For an application, it's the different operating systems and different interconnectivity that they may or may not have. A phone is outdoor portable. And we can define function and environment in great detail, and we often do with engineering reference specs or detailed specifications or environmental descriptions that includes usage. How often are we going to use the phone? How often is this product line going to produce products? Bottles per minute in a bottling plant, for example. Those parts, function and environment, are often assumed and generally fairly well known. Not perfectly. But the probability of success. MTBF is a piece of this. It's the inverse of you can calculate probability of success with MTBF if MTBF is a good number, but you also need what duration. So this is the couplet I typically look for is, what's the chance that this phone will last 1 year? What's the probability of success over some finite duration? Oftentimes I advise people to use multiple couplets. The early life failures, for example, may be very damaging to your brand and product acceptance in your market. So choose a 1 month period of time. I want 99.5% of my products to go into service and function for at least 1 month. And I want 98% to survive 1 year and 95% to survive 5 years, for example. But each of those couplets are, the function occurs in the customer's environment and use conditions, and then the probability and duration. And you can have multiple of those. But these are tied to business objectives or customer requirements directly. So the warranty is the easiest example. If I have a 1-year warranty, I probably am budgeting a certain warranty expense. Well, that directly relates to my failure rate and my cost per failure. So if I have a warranty budget, I can back out knowing what's the cost per failure, how many failures I can afford. And that sets this probability of success. So if I can only afford 2% of my products failing, well, that implies a 98% reliability over your warranty period. And by similar thought processes, connecting that to the early life failure period or installation period, or to a useful life period. So that it's similar, Vipin, to the bathtub curve, but it's without any lines or distributions. It's connecting your business objectives or your customer requirements back to your reliability objectives and quantifying it without any distribution associated with it. So MTBF, if that's the only thing I have, I tend to have to assume it's a constant failure rate or an exponential distribution. A fit rate or annualized failure rate also implies that it's constant over the entire duration. That's rarely ever true. So using a distribution-free way to talk about reliability, the couplets of probability and duration, is one good way to avoid making assumptions that may not be useful for you. So I'll see if I can get past the MTBF slide here without getting on that soapbox. And I'm looking at the time, so I'm going to, here I was going to ask you to do what I do in my classes I teach, is draft a reliability goal. So I'll leave this to the interested student, but can you say in one sentence your reliability goal? And I'll give you one example. Say an iPhone provides email and internet connectivity in an outdoor portable environment with a 99% reliability over the first month, a 98% reliability over the first year, and 95% reliability over 5 years. That is a succinct and meaningful goal for the entire team. And there's homework behind that, is how do you connect that to your business? Can I reference in engineering specifications and user environment and user use studies, things like that, to get the details I need to actually implement this and interpret it? One caution is, yeah, Vipin, I like it. B10 at 50,000 hours. So you have the couplet. It's the probability and a duration, right? So it's, I would, instead of B10, I would say I want a 90% probability of going 50,000 kilometers. Engineers understand percentages intuitively. Most of them do, even managers. No offense to the managers in the group. But make it as clear as you possibly can. Part of one of the issues with our industry is that we use the term reliability. And if you take a look at advertising, for example, they use the word reliability in a completely different way. They mean trustworthy or dependable or will be there when you need it. In some cases, it almost means availability. But we have a different definition of it. So being very clear and touching on all four elements helps avoid any confusion of what we're talking about, and also gives us a way to measure it. So those are generally very good things. So I'm going to mention a handful of the tools just quickly here, and then we'll get into some more questions and answers. once you have a goal, top-level goals, break it down. Break it down to the major subsystems. I'm sure you're familiar with reliability block diagrams for series and for parallel structures and stuff. They can be very, very simple. And if I saw one time a technical engineering manager did the apportionment for his team. So he took I think it was a 95% over 1 year goal, and they had 5 major subsystems. And I'm using a fictitious example because except it was a real case because I can remember the math. And so he didn't have any prior knowledge of what the historical performance were of these 5 different elements. So he gave it a straight line apportionment. Everybody had the power supply, the CPU, the hard drive, and so on. Each had to have 99% reliability over 1 year so that the math would work out for the system. It was pretty intuitive. And then the program manager, she looked at the rest of the team, and the power supply guy was saying and looking upset because there's no way he was going to make 99% over 1 year. The power supply just wasn't going to make it that way. But the keyboard and mouse guy for this computer system, he was happy. He knew he didn't have to worry about that goal whatsoever. He had room. He didn't have to worry about it. So what that program manager did, not the reliability engineer, which there wasn't a reliability professional on this team, but this very simple series model and basic apportionment then started the discussion of, well, power supply, well, what reliability can you get to? And how much would it cost to make improvements? And now they started the discussion of balancing cost, which was a major priority for that program, with the balancing of reliability across the allocations of their systems. It stopped the individual silos optimizing, and it started the discussion across the table of, well, if I give up a little bit of cost, I can afford more reliability somewhere else. So think about it. Even a very simple model can drive a discussion that can be very, very useful for the development team and for the management of that team. Measurements and estimates. I've lost count of how many times people say we have a reliability goal. It might be 98% over 5 years. And then I says, well, how do you measure it? It says, well, we wait for customers to tell us how good it is. Like, well, there's a whole spectrum of ways to measure reliability that does not have to wait until your customer finds all the failures for you. I euphemistically call that the Microsoft method. But the notion is that even an engineering estimate early in a program is of value. Let's use that. Let's put it in the model. Let's analyze where that comes from. How certain is that information? Can we get vendor information or publicly available data or use a database? We know that it's not perfect. It's not our product. It's not our customers. Yet it gives us an indication of where we're at. Can I get vendor data or test data that show the failure mechanisms and their behavior over time? It's a little bit better. I'll do some internal accelerated life testing, fill in some more numbers. I'll use field data from similar products and similar systems and or even barter for information with other companies that have similar technologies. But the idea is that there's a spectrum of measurements and estimates. In a reliability, we have to know where we are to balance the decision point with time to market, cost, and function. If we don't have a reasonable estimate, it's very hard then to weigh the pros and cons of, do I invest in a more reliable component or less reliable is okay? So I need a decent feedback mechanism back into the program. And this is part of that structural challenge in many organizations to get this right. Risk identification. I didn't say FMEA, right? Yet engineers do FMEA intuitively. They design away from failures. So FMEA coordinates that and prioritizes it and balances it out across your organization. But also halt testing is a risk identification tool. It discovers failure mechanisms that we may not have known about before. So broaden this definition in your program of what we mean by risk. And some organizations call it hazards analysis, and some call it FMEA, and some call it due diligence. Whatever you call it, there's an active interest, and I saw some of the comments earlier, is that's a big part of what we do, is uncover where the dangers are, what the risk is, what's the challenges. Now part of this also is in that rest of that definition of reliability, it includes the environment. Is how are our customers going to use this? Where are they going to use this? What loads and stresses and temperatures are they going to use it? How often are they going to use that? Are we clear inside the organization of how all of this information is used to create designs and estimate reliability when we start looking at stress strength calculations and so on? So it's a big piece of that. The gap analysis part is back to that model. Let's say I had the 5 elements of a computer: hard drive, power supply, motherboard, display, and keyboard system. Well, the power supply is this large band over on the left where they're saying, hey, we've got a big distance between what our goal is and what we can do. Where the power supply is over on the right in the noise saying, hey, we've got plenty of room. Well, do I need better information to make a better estimate? What do we need to do to get better information? Field data analysis, surveys, internal testing, working with vendors. How do we get better information? Or the risk is that we've got good information, it just can't, it's not good enough. It doesn't perform as well as what our objective is. Well, what are our options? Different technology. Do we use redundancy? Do we use a more reliable, more expensive type components or elements? What's the trade-off? What's the balance here? And at some point, if we're looking at reasonable estimates and we're still not meeting our overall goal, well, what's the risk to our program? Let's go back to our management team and say, here's where we are. We're going to be 0.5% more failures than we expect. We need to adjust the warranty or change the service, and we need to change the marketing and customer perception setting that goes on in product development. So part of this gap analysis I'm trying to illustrate is internal to the team and the project to help make balancing decisions and coordinate the reliability of your program or response at decision level, but also reflect it back out to the rest of the organization, is give us a clear understanding of where we are versus the goal and where the risks to achieving that goal really exist. Testing, in my mind, this is a last resort. A lot of us do testing. A lot of us like to say we break things. I think that's one of my favorite ways of describing what we do. Yet, that's not the most valuable thing we do. Testing, in my mind, is expensive, and it's a difficult way to get an answer. It's fun. I enjoy it. I've done plenty of testing over the years. It's how I got started in reliability engineering. Somebody asked me to do an accelerated life test. I didn't even know it was called that at the time. Yet, it's often a very difficult way to get the information you need. So elements like physics of failure, where you do testing and evaluations and study to understand the failure mechanisms such that you can avoid testing in the future. I think we should be working towards minimizing testing to only the essential elements. It's still going to be a part of our world. No worries there. You don't have to sell your chambers. But in my mind, our biggest value is well before we have prototypes. It's in the specifications and in the definitions and in the modeling and at the point of decision during the design process. Testing helps us to validate or confirm what we're doing or to answer specific questions. And my last note on testing is, if you're doing testing just because you always do testing, you should step back and ask, well, where's the value? What decision is this influence? What information is it providing? And if there's not a good answer there, stop doing the testing. Just mentioned failure analysis and FRACUS, the failure reporting and corrective action type systems. Part of our program and management of this is to get to the root cause and the triage and prioritization of all of the details that we find that could lead to field failures. I think many of you are familiar with these two concepts. I'm going to move on here. So value. I've got a poll, if I remember where I put it. And I know I've talked about value quite a bit. So I believe this is open. Pick one or more of these that you use to quantify the value of reliability. So, cost reduction can do a couple different ways. Reduce failure rates in the fields and reduce warranty costs. Reduce downtime so that you can produce more revenue. It's both good ways to think of that one. Customer satisfaction improvement. I ask my students every year is what's the biggest contributor to the expense or the cost of poor reliability? And in my mind, it really is customer satisfaction. It can put you out of business. If customers don't like your products because they're not reliable, they'll move on. It's often, though, difficult to quantify. A 1-point change in customer satisfaction, what does that translate to and how much I have to change the reliability of the product? So in some places they have those studies, and others they don't. The other part is risk reduction. And I agree with that being a high hitter for the value. I've heard it said a few times, especially the program managers that's under a lot of stress to get this product launched. It's the uncertainty about how reliable a product is keeping me up at night. So by getting a decent model, creating a coherent assessment or estimate of the design's performance in the reliability realm would help them to sleep at night. It reduces the risk of delaying the program, for example. Those are very good. So, and I'm not sure, let me see, let me end the poll here. Oops. Back to poll. So let me move on. I find that working on value and connecting the expense of, say, doing a halt test to the expected return or value out of that helps me to get buy-in to do the halt test. It helps people understand why we're doing it, and it helps to justify to my boss, when I was working at HB in particular, why I was there. It wasn't just doing halt tests because it was required. It was doing it because we discovered failure mechanisms that reduced the risk of delaying the shipment. It reduced the failure rate in the field, which improved customer satisfaction. And then we could quantify each of those things in terms of dollars or profit. So I'm going to wrap up here is that a couple other elements I'm going to talk about in future installments of this program and this course is program assessment. How do you tell where you are and what's working and what's not working? There's a relatively simple way of going through and understanding where you stand on a program, a maturity matrix. And one of the handouts, and I'll bring the handout link here in a minute, because I know this could be an eye chart on many of your screens, but the idea of maturity is some organizations don't know how to spell reliability and it just happens to them. They don't know what it is. Some say it's important and they do some testing, they do some work and they pay attention to it. They may not measure it well, they may not set goals well, they may not do testing well. Stage 3, they're very reactive. If they get a failure, they jump on it. They've got a very good fire department. They do lots of testing, but they're not quite there yet. They always seem to sense that they're responding to customer complaints rather than predicting them. The difference between 3 and 4 is reactive versus predictive. And now we're starting to get command of our program, and we're getting the highest value for every task we do. When I first did these assessments and surveys, my thought was that the more you did, the better your program, the lower your warranty. And that wasn't true. The highest warranty costs was the uncertainty people. And it went down to the stage 5. There was a couple companies we dealt with that were very, very good at what they did and very proactive. But they had almost the same amount of testing as the stage 1 group. They did very little testing, which was a major driver of cost of doing product development, was the prototyping product testing. The stage 3 group did a lot of testing, and it was very expensive, but they weren't getting as much value for it because it wasn't as well connected into making decisions. So I certainly will spend more time on this concept in other sessions. So in summary, I know I covered a lot of material and a lot of concepts, but core to this is that reliability engineering has a broad scope, and we work through influence. By quantifying the value of what we do and articulating the structures and the information such as cost of downtime, it enables other people in the organization to make good decisions. So setting those together really makes a difference. So I'll leave this slide up. If you're interested in pursuing the rest of this course, I'm going to pull up the conclusion slide here. There's a link in the lower right where it's information lists for the reliability management course. It's a free list. I'm going to send out more information about the rest of the course, and once I get it set up and the links created, I'll do that. I'm still working on doing a monthly webinar like this that's free. So hopefully I'll see many of you again. I see a couple of regulars here. But let me take a look at some of the questions. I see a question, how do you decide sample size and test duration for a reliability test? It's a good question. Oftentimes it's, well, how accurately do you need to know to make a decision?
The meeting is now over. All the participants have been disconnected.
Hopefully, my recording just means that we lost the phone bridge, but let me know if you can still hear me. Let's see, I think the chat window is still open. Okay, good. Yeah, I don't know why the structure behind here after some time decides she's done and she lets us go. But I'm still on the line. I'm going to end the recording here. Well, I'll leave it running and answer any questions you have. There's a question and answer tab and the chat window, and I'll try to stay connected to both of those as long as you have questions. I do have some more time. It ran a little bit long. Sorry about that. So sample size and test duration. Test duration is usually a function of what's the failure mechanism. So if I have a cable that I know is going to bend, say 90 degrees over some mandrel once a day, well, if I can create a structure that'll do that more often per day, say 10 times an hour, I get a 2400x acceleration, and so I can replicate the number of bends over the expected lifetime relatively quickly. It becomes more difficult when a product's used 24/7, say a server at say eBay or Amazon. It's on, it's running, it's processing information and orders 24 hours a day. I don't have the luxury of just compressing time, so I have to use accelerated testing. So increase stress for the failure mechanisms that are expected to occur. That helps me set the duration. It's a separate question for how many samples to run. And there again, it's, well, how accurately do I need to know it? What's my decision point from my acceleration, from my reliability model? So if overall my product is 95% reliable over 1 year, my power supply may need to be 99% reliable over 1 year. And so if I'm testing power supplies, do I need to know with certainty to choose this power supply that it's at 99% or higher reliability? Well, if so, that may require more samples. If I make a decision that if it's as bad as 95%, I don't use that one, I have a less restrictive test, so maybe I can do that with fewer samples. So it's always back to that decision. how accurate do I need to know that information? And who's going to make that decision, and what risk are they willing to take? So the idea is to not use a rote number. Don't use a standard that says, oh, test 7 samples for 1,000 hours and you're good. If that has no relevance to the acceleration factor or for the failure mechanism that's in your product or to the decision that you need to make, it's of little value. So it's an excellent question, but for each test, it should be considered of who's going to make the decision and what information do they need to make a good decision. And certainly there's a whole lot more information on sample size test duration, accelerated testing, testing in general. I'll come back to that in another part of this course, and most likely in another webinars program at one point or another. Yeah, and George, I think I have it up now as the maturity matrix along with the slides, and I have a paper that I created for RAMS, a tutorial at RAMS is in the download section. The slides are available in the download section, and the matrix is available in the download section. And all you need to do is click on which one you'd like, and then the download file button should become available, and you can pull it straight down.